Everything around us, from the air we breathe to the stars in the sky, is made of atoms. These atoms are incredibly small, so tiny that they are invisible to the naked eye. Yet, they are the building blocks of all matter, forming the foundation of everything we see and touch. From the simplest elements like hydrogen and helium to complex compounds and materials, atoms are the essential units that make up the universe. These tiny particles are the fundamental building blocks of matter, the smallest units that retain the properties of an element. Atoms combine in various ways to form molecules, which in turn make up the substances we encounter in our daily lives. Whether it's the water we drink, the food we eat, or the air we breathe, atoms are at the core of it all. The smallest unit of an element that retains the chemical properties of that element is an atom. Each atom consists of a nucleus made up of protons and neutrons, surrounded by a cloud of electrons. The arrangement and number of these subatomic particles determine the characteristics and behavior of the atom. Imagine a grain of sand. It contains billions upon billions of atoms, each one a miniature universe unto itself. These atoms are in constant motion, interacting with one another in complex ways. The sheer number of atoms in even the smallest objects is mind-boggling, highlighting the incredible scale at which these particles operate. Each one a miniature universe unto itself, atoms are fascinating in their complexity and diversity. They can bond with other atoms to form molecules, creating the vast array of materials and substances that make up our world. Understanding atoms is key to unlocking the secrets of the universe, as they hold the answers to many of the mysteries of nature. Understanding atoms is key to unlocking the secrets of the universe. By studying these tiny particles, scientists can uncover the fundamental principles that govern the behavior of matter and energy. This knowledge has led to groundbreaking discoveries and technological advancements that have transformed our world. The concept of the atom has been around for centuries, with ancient Greek philosophers first proposing the idea of indivisible particles called atomos. These early thinkers laid the groundwork for our modern understanding of atomic theory, even though they lacked the tools and technology to observe atoms directly. With ancient Greek philosophers first proposing the idea of indivisible particles called atomos, the journey of atomic discovery began. Over the centuries, scientists and researchers have built upon these early ideas, developing sophisticated theories and experiments to explore the nature of atoms. However, it wasn't until the 20th century that scientists were able to peer inside these tiny entities and discover the strange and wonderful world of quantum mechanics. Advances in technology, such as the development of powerful microscopes and particle accelerators, have allowed us to observe and manipulate atoms in ways that were once thought impossible, and discover the strange and wonderful world of quantum mechanics. This branch of physics has revealed that the behavior of particles at the atomic and subatomic levels is governed by a set of rules that are vastly different from those that apply to the macroscopic world. These discoveries have challenged our understanding of reality and opened up new avenues of research and exploration. What they found was that the laws of physics that govern our everyday world break down at the atomic level, replaced by a new set of rules that defy common sense. These quantum rules describe phenomena such as superposition, entanglement, and wave-particle duality, which have no counterparts in the classical world. Replaced by a new set of rules that defy common sense, these principles have profound implications for our understanding of the universe, as they suggest that reality is far more complex and interconnected than we ever imagined. The study of quantum mechanics continues to push the boundaries of science, revealing new insights into the nature of existence. This journey into the atom takes us deep into the realm of quantum mechanics, a branch of physics that explores the often counterintuitive behavior of matter and energy at the atomic and subatomic levels. By delving into this microscopic world, scientists are uncovering the fundamental principles that govern the universe. A branch of physics that explores the often counterintuitive behavior of matter and energy at the atomic and subatomic levels. This exploration has led to the development of new technologies, such as quantum computing and advanced materials, which have the potential to revolutionize various fields and industries. By understanding the bizarre yet beautiful principles of quantum mechanics, we can begin to grasp the true nature of reality. These principles challenge our conventional notions of space, time, and causality, offering a deeper understanding of the universe and our place within it. We can begin to grasp the true nature of reality. As we continue to explore the atomic and subatomic realms, we are likely to uncover even more astonishing truths about the universe, pushing the boundaries of human knowledge and expanding our understanding of the cosmos. At the heart of every atom lies the nucleus, a dense core composed of protons and neutrons. Protons are positively charged particles, while neutrons carry no charge. Together, they give the nucleus a net positive charge. The number of protons, known as the atomic number, defines the element to which the atom belongs. For example, all carbon atoms have 6 protons, while all oxygen atoms have 8. The nucleus is incredibly small compared to the overall size of the atom. If an atom were the size of a football stadium, the nucleus would be like a tiny marble sitting at the center. Despite its diminutive size, the nucleus contains almost all of the atom's mass. This is because protons and neutrons are much heavier than electrons, the negatively charged particles that orbit the nucleus. The strong nuclear force, one of the 4 fundamental forces in physics, binds protons and neutrons together in the nucleus. This force is incredibly strong at short distances, overcoming the electrostatic repulsion between the positively charged protons and holding the nucleus together. Unlike the well-defined nucleus, the electrons in an atom don't follow precise orbits like planets around the sun. Instead, they exist in a cloud-like region surrounding the nucleus, constantly in motion. This region is often referred to as the electron cloud, a term that captures the dynamic and somewhat unpredictable nature of electron behavior. The electron cloud is a visual representation of where electrons are likely to be found at any given time. Unlike the predictable paths of planets, electrons are governed by the principles of quantum mechanics, which introduce a level of uncertainty and probability to their positions. Their exact positions and momenta cannot be known simultaneously, a fundamental concept in quantum mechanics known as Heisenberg's uncertainty principle. This principle highlights the intrinsic limitations in measuring quantum particles, making the behavior of electrons both fascinating and complex. The behavior of electrons is governed by their energy levels. These energy levels are like the rungs of a ladder, each representing a specific amount of energy that an electron can have. Electrons can move between these levels, but they cannot exist in between them. Electrons occupy specific energy levels within the atom, much like people can only occupy specific floors in a building. This analogy helps us understand that electrons are restricted to certain energy states, and their movement between these states is what drives many of the atom's properties. These energy levels are quantized, meaning electrons can only exist at discrete energy values, not in between. This quantization is a key feature of quantum mechanics and explains why electrons behave in such unique ways compared to larger classical objects. When an electron absorbs energy, it jumps to a higher energy level. This process is known as excitation, and it requires a precise amount of energy to occur. The electron cannot partially jump. It must move entirely to the next level. When it releases energy, it falls back down to a lower energy level, often emitting light in the process. This emission of light is what we see in phenomena such as neon signs and fireworks, where electrons are constantly moving between energy levels. The arrangement of electrons in different energy levels determines the atom's chemical properties. This configuration dictates how atoms interact with each other, forming the basis for chemical reactions and the creation of new substances. Atoms with their outermost energy levels completely filled are generally stable and unreactive, like the noble gases. These elements are often found in their pure form in nature because they do not readily form compounds with other elements. Atoms with partially filled outer energy levels tend to be more reactive, as they seek to gain or lose electrons to achieve a more stable configuration. This drive for stability is what fuels chemical reactions, leading to the formation of new molecules and compounds. This interaction of electrons is what drives chemical bonding and the formation of molecules. Through the sharing or transfer of electrons, atoms can achieve more stable configurations, resulting in the vast array of chemical substances that make up our world. To understand the strange and counterintuitive world of atoms and subatomic particles, we need a new set of rules. This is where quantum mechanics comes into play. Unlike the classical physics that governs our everyday experiences, quantum mechanics delves into the microscopic realm, revealing a universe that operates on principles vastly different from what we are accustomed to. Quantum mechanics is a branch of physics that governs the behavior of matter and energy at the atomic and subatomic levels. It introduces concepts that challenge our traditional understanding of reality, such as superposition, entanglement, and wave-particle duality. It differs drastically from classical physics, which describes the macroscopic world we experience daily. Classical physics, rooted in Newtonian mechanics, provides a framework for understanding the motion of planets, the trajectory of a baseball, and the mechanics of everyday objects. Classical physics treats objects as having definite properties and following predictable paths. For instance, if you know the initial conditions of a system, you can predict its future behavior with great accuracy. A thrown ball, for example, follows a parabolic trajectory, its position and velocity knowable at any given time. This predictability is a hallmark of classical physics, making it intuitive and reliable for understanding the macroscopic world. However, in the quantum realm, particles like electrons behave more like waves, their properties described by probabilities rather than certainties. This wave-like behavior means that we can only predict the likelihood of finding a particle in a particular location, not its exact position. This inherent uncertainty is a fundamental principle of quantum mechanics. Known as Heisenberg's uncertainty principle, it states that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. It's not due to limitations in our measurement tools, it's an intrinsic property of the quantum world. This principle challenges our classical intuition and forces us to rethink the nature of reality at the smallest scales. Imagine trying to pinpoint the location of a wave on the ocean. Waves are dynamic and constantly changing, making it impossible to define their exact position at any given moment. You can talk about the wave's properties, its height and wavelength, but pinning down its exact position at any given moment is impossible. This analogy helps us grasp the elusive nature of particles in the quantum realm. Quantum mechanics embraces this wave-particle duality, accepting that particles like electrons can exhibit both wave-like and particle-like behavior, depending on how they are observed. This duality is a cornerstone of quantum theory, illustrating the complex and often paradoxical nature of the quantum world. This duality is just one of the many mind-bending concepts that make quantum mechanics so fascinating and challenging to grasp. From entanglement, where particles become interconnected regardless of distance, to superposition, where particles can exist in multiple states simultaneously, quantum mechanics continues to push the boundaries of our understanding and redefine the very fabric of reality. Superposition, embracing uncertainty, one electron at a time.